on the chat, right? Good afternoon, good evening, rather, everyone. This is Vishal Ahuja, I'm co-founder and CEO of Techlans. With this, let me start first the session which everyone is, I think, waiting for: motor sizing and control selection. So the agenda, what today's session I'm going to cover is, I'll start with basic fundamentals, which are there, maybe a couple of minutes. Then we'll go deep dive in the case studies, right? We'll talk about what is basically EV motor when you talk about why it's different than general purpose motors, how the motor sizing is done, different motor types which are there, segment specific need. I also come from 12-year experience in the automotive industry only, right? So I'll talk about different segment specific needs which are there, different motor selection criteria. Then we'll take a case study and understand the different efficiency impact on the basically EV perspective, right? Then voltage current rating. We'll talk about control selections also, right? Before that, do you everyone feel excited about this agenda? Give me yes in the chat. I would like to see that everyone is at least awake by this time if people are looking forward to this. Great. Very difficult job Priya has given to me to keep everyone awake at this point of time.
We've kept the most anticipated session.
Yeah, thank you, Priya. Yeah, okay. Right. So let's start with this. And first of all, the most common things which you see, right, as per part of your daily life is a fan motor, right? And what is a different motor? What you see most commonly in your daily lives, you might have seen a toy motor, right? Which is your simple DC motor, right? But how a EV motor is different than normal motors what we use in daily applications, right? So we have a powertrain, which is electric powertrain. So what makes it so unique? We have been using the motors for pumps, fans, toys from long decades, right? So why there's so much buzz around electric vehicle motor? Why there is so much innovation required with that, right? Let's understand that first place. When you're looking for a engine, right? When you buy a car, you expect the car to run for 20 years, 25 years, right? You don't expect it to break down on the road. Same thing expectation from the motor also. You might have seen the ceiling fan which you use or the electric toy motor which you use. They don't may last for that long, but you don't expect your vehicle to break down, right? You want that vehicle to go last long for a very long period of time. And apart from that, in the fan, you have a normal regulator to control, or you have a remote control car to control this one speed of the way, this one motor, right? But you want very precise control of your motor. That was make also make EV motor different. You need very high torque. The normal toy motor or ceiling fan motor may not be having high torque, but the EV motor are supposed to have very high torque and high power, and they are supposed to take you till 250 km/h speeds also, right? That is something which you're looking forward to. Then you need enormous amount of efficiency also in the EV motors. Reason being, you are working on EV and the batteries are expensive. So you want efficiency which is so good on the vehicle level so that my battery requirements can come down. We have a case study on this also. We'll talk about in much more detail, right? As well as you don't want this motors to be as bulky as your pump motors, right? Which you might have seen three-phase pump motor you might be having using at home. You want this to be as compact as lightweight, which Sajal also covered, right? Why their motors are different because they're very compact and lightweight, right? And then you don't want your vehicle to make huge amount of noise. You might have used a pump motor at home, right? When you see the pumps are running, they make huge amount of noise. You don't want these things to happen on an EV motor. So these kind of requirements which are there on the EV motor, which makes them a different in terms of application, right? Let's understand from a project perspective when you're trying to make a vehicle, right? Let's consider example. So first and foremost thing is the project level target. So let's consider example, we are trying to make a two-wheeler. The first and foremost target for a project perspective would be your top speed and acceleration. What kind of vehicle character you want to give? What's the gradient and payload your vehicle can take if you're thinking about making a cargo vehicle especially, right? So Mr. Roy talked about it, the Monter Electric, and Mr. Amitabh Saram also there. The gradient payload matters a lot. Then the range, most important buzzword of EV, right? You want to decide how much kilometer range you want to give. It's like a very old tradition of calling it the more sugar you keep, the more sweet it become. The more battery you keep, the more sweeter it become. But it's not always the case. We'll talk about it at the end. Then what's my warranty target? So Mr. Akshay said, like when how the things have evolved over the time, right? Earlier people were okay, we are making the motor, but now people are asking for 10 years, 15 years kind of warranty, and they're asking for 1 lakh, 2 lakh kilometers kind of warranty also, right? And then we are Indians, right? We want everything at very cheapest cost, right? Obviously, because we have to meet that vehicle level targets. Based on these project level targets, first you derive the engineering specs based on simulations, preliminary simulation, 1 day simulation, where you decide what should be my motor power, motor torque, battery capacity, system level voltage, and weight of the vehicle, right? Or weight of the particular pack. So these are the first engineering level specs you derive. After that, you go one step deeper, understand, okay, now what's my power current rating, AC current rating, DC current rating, what kind of packaging I'm going to use. I'm going to use a mid-drive motor or hub motor based on your trade-offs, what you have, based on cost, based on vehicle dynamics, based on comfort, speed, right? Then you decide, okay, now for when you do the project level target setting, you divide that onto component level target setting on cost, right? Then you design what kind of motor I should use. Should I use a axial flux motor? Should I use a permanent magnet motor, induction motor? We'll talk about all those things. Then what will my thermals will look like, how my heat generation is happening, what's my kilowatt, can I do for go for the liquid cooling, can I go for air cooling? Mr. Ramesh Karla given an example, when they made the motor and they made without fans, people are saying, okay, this will not work, it will heat up, right? So these kind of decisions also you have to make. What's my thermal level requirements? Then what's the efficiency you are expecting also from the powertrain level? And one thing Mr. Amitabh Saran said, when people may overlook is the algorithm and software. This is also very important. What kind of functions you are expecting your motor controller to solve as a complete system? What you're expecting the system to solve? What kind of algorithm? Like for the L5 application, most of the time they don't use the VCU. The VCU functionalities are embedded in the motor controller itself. So you have to give these kind of inputs also, right? Now, very basic and foremost thing, I think most of you know that for deciding the motor size, the first and foremost thing is to understand what's my force level requirement when the vehicle is traveling, right? So this is the most common thing which everyone knows, that there is a rolling resistance force, aerodynamics force, inertial force, grid resistance force, right? So when combine all these things, you get a total tractive force, the force which is required to move the vehicle in forward direction at different given speeds, different acceleration levels and all. This is gives you around 80% accuracy, right? Most of the people when they start doing the sizing of the motor or their system, this is a basic thing they use. But there are much more things what differentiate uh, like you can say that it's very easy to score 80% marks, but scoring 95% marks or 100% marks are difficult. Similarly, when you're trying to correlate your tractive force which is running on the vehicle, when trying to correlate a range of the vehicle, there are some other parameters also which makes huge difference. Now that what differentiates from an outstanding OEM from a normal startup, right? Which is your other losses which are coming from your gearboxes, brakes, bearing, impact of temperature, pressure on the tire, like surface resistance, impact of air densities, and all those things which come into play. These are dynamic factors. When you go in detail, then you understand these are the additional thing which you need to consider while doing your tractive force estimation, and what this differentiate from a good simulation to a normal simulation, right? To from a beginner level simulations, right? Based on these things, based on when you have the total tractive force requirement, based on that you decide, okay, first you have the gradient level target, right? For a GVW condition I have this much gradient. Then you decide for meeting those gradient requirement as well as my performance requirement, what's my torque level which is required, because force torque is nothing but force into radius, right? You know that my tire radius is how much, you know the force, you get the torque very straightforward. Then based on meeting your max power condition, like max speed condition, when you're trying to drive a vehicle, you understand, okay, what's my max power requirement? It can come from max torque and base speed also, but typically comes from max speed condition. What's the max speed of the vehicle you want to drive and what the acceleration level you want to give that condition, right? Then you get these kind of thing. Based on that, you also get your rated, because The motor torque, which is giving the max torque and the max power, these are pulses. But you don't understand. Imagine you are going on a ghat level, right? In a gradient condition. People forget that kind of situation when you're designing the vehicle, right? Imagine a commercial vehicle when you're designing that vehicle when it's trying to climb a gradient, for suppose from one ground place to is going to OT, or from this place which is going to Korekanal, right? There is a gradient which is continuous in nature. So that time your peak torque will not decide how long your vehicle will go. It's a continuous torque which is required to pull that vehicle at that gradient, right? So this is something important. We should not miss it out, and the vehicle will be keep on operating without any like issues because of thermal deratings and all. So these things are decided in very beginning, right? Let's understand once you decided what kind of motor torque you want, what kind of motor power you want. Now it's time to decide what kind of motor also you want, right? The preliminary level study is done, but now you want to go deep. You have too many applications based on packaging. For a two-wheeler, you have hub motors, you have mid-drive motors. In the four-wheeler, we call it central drive. And some motors are like swing arm mounted motors. The classical example is Chetak, right? Hero Vida also. Then you have rigid axle mounted motors also, like, which is used in e-rickshaws and all, right? So based on packaging also you have these kind of things. Then based on magnetic flux, you have radial flux motors, axial flux motors. So Mr. Ramesh also talked about it. I know him personally because of axial flux motors only. He started developing axial flux motors, and I think torque motors also was doing axial flux motor beginning, right? Then you have transverse flux motors also. So based on magnetic field also you have different kind of motors. Based on supply power, you can use DC motor or AC motor like BLDC motors. I will talk about all these things, right? Brushless DC motors, because brushed DC motors are not used for the EV applications. Then you have based on number of phases, single phase motor not used in EV application. You have typically three-phase motor, and now trend is going towards using your multi-phase motors also when you're talking about sports car and very high efficient motor, right? This trend is also coming up now. Then based on operating principles, you might have heard of PMSM, surface mounted magnets, internal mounted magnets, SRM, induction motor, WSRM, SynRM. I think uh, people covered about this as well, right? They have so many applications. It's not like that you have to choose either of them. A hub motor can be a permanent motor, right? Or can be DC motor, right? It can be radial flux motor, right? So it's based on the application. You have to choose wisely what meets your requirement. Now, coming on the application, your requirements are different for different applications. As a person, I have worked on all the three applications. I worked with Mahindra for around 8 years, where I was working on light commercial vehicle, passenger vehicle, all the EVs. I had my own startup on three-wheelers, cargo vehicles. Then I worked for two-wheeler startup also, right? Coming from having experience on all the three industries as a whole, as well as heavy industries also. For each and every application, the requirements are different. For a two-wheeler, the typical range requirement on the road is around 80 kilometers. People may argue that, okay, I want 150 kilometer range, I want 200 kilometer range. I'm talking about typically which are used in the market as of now, right? GVW is 300 uh, kg. Then acceleration requirement is 3.9 seconds approximately, 5 second, 4 second, 2 seconds, right? Speed is 80 kmph. Torque requirements are not that much. Power requirement is not that much as compared to three-wheeler and four-wheeler, right? Where the four-wheeler speeds can go up to 150 kmph, right? Very high GVW application. The buses go further higher, right? The range people want around 1 miles, right? People talk about it, 1,000 miles or 1,000 kilometers of range, right? People are talking about that as well now. Now, then you have multiple choices as we discussed. You have hub motor choice, mid-drive motor choice, rigid axle mounted for the cargo segment, as well as MG Comet is the classical example which use rigid axle in the back also, right? And you have obviously center drive motors for the four-wheeler, which is widely used. So first and foremost is in what application your vehicle is. Based on that, you have to decide. Because because while you're choosing this, you have option of multiple choices, right? So a perfect motor, what you want from a perfect motor is at lowest cost, you should have very least amount of control efforts. You want very minimum maintenance. You want very high speed applications. The torque density, power density should be very high, right? And the efficiency in the base speed condition as well as field weakening application should be very high. You want power factor to be very good. You want least noise. You want least torque ripples. This is what you expect, right? I want everything from a motor. But that is not physically possible, right? Because there will always be some trade-off. Let's talk about BLDC motors, right? Because of permanent magnets, the cost is not so great. But control effort, maintenance, torque density point of view, they're quite good. Power factor is also good, but they also make some noises, right? Torque ripples are also higher. Then you have PMSM, very good in terms of torque ripples, very good in terms of noise, right? Very good power density. Everyone is talking about power density, torque density for PMSM. That's why people are using it, right? And but control efforts, you need to have a very good FOC based controller over there, and the cost is also higher because of permanent magnets, right? Then you have induction motors, very good for the high speed application. Cost wise, they're better than your induction PMSM motors, right? Noise wise, they're also good. In the field weakening zone, their efficiency is better. We'll talk about this in much more detail, right? Then power density, torque density, they're not so great, right? Then you have SYN RM motor, right? In that case also, the high speed application, they're not that much used, right? Their efficiency in the field weakening zone is not so good, but cost wise, if you see, they are the best. No one is able to beat them in terms of cost, right? Let's talk about the SRM motors, synchronous reluctance motors also. There you have some issues over there, right? The SRM. This is basically a comparative study. Some people are using, as someone talked about it, hybrid of combination of permanent magnet and CNRM also, SRM also, which is called hybrid motor, which actually take care of your torque density, power density, and you try to get the mix of both. I think Mr. Ramesh Nalka also talked about it. Hybrid motor, 60% magnet, and remaining as SRM combination of that, right? So that gives you some kind of balance where you're able to mitigate the cost, but still the control efforts are quite good. It's not easy to control that SRM, right? Let's see now from the efficiency zone perspective, right? It's very interesting to see that when you decide that, okay, my peak efficiency, if you see this, in most of the three application, which is your PMSM motor, induction motor, and SRM, the peak efficiency is somewhere around 97. This is 97, this is 97, and this is also somewhere around 97. The difference is the efficiency zone, the operation zone, what makes it different. For if you see this, the PMSM has a wider efficiency zone in a larger band of operation, right? Whereas your induction motor has a peak efficiency in very field weakening zone, very high speed and low torque conditions. Your SRM is at mid torque condition and high speed condition, you have a peak efficiency zone. Now, for the Indian application perspective, right, from the stop and go situations, if you see that your induction motor may not work because in traffic condition, this will offer a very bad efficiency. Now, the induction motor will be very useful in kind of your railways application where the railway tracks, if you see, they offer very less resistance, right? The major resistance come from the inertial resistance because the tire, whatever the steel tracks which are there, they offer very less resistance, tire resistance, right? So in those applications, when the speed is continuous, you always driving at high speed and always nominal torque. These kind of motors are very good. If you see in the Indian railways, mostly they're using induction motors that way. And if you see the PMSM motor, it offers you in a wide range, a wider band. Now, people, when you are trying to get the motor, if you're just asking for the max efficiency, you will lose out because the number will look the same. What you are looking for is a cycle efficiency. Now, as I talked about it, the two-wheeler, three-wheeler, four-wheeler, the applications are different, right? Now, based on your application, you have to decide what your cycle is. You might be operating in WLTP cycle. Your max speed might be 45 kmph for three-wheeler, for a cargo vehicle. For a four-wheeler, you might max speed might be 120 kmph and all. So you have to perform the cycle as well as on which countries you are going to supply that vehicle. So it's a system or a vehicle level approach which you have to think of. Now, just to mitigate this the issue, I'll talk about some more thing. Sometimes people think the PMSMs are extremely efficient. People don't look below this actually. When it's a low RPM zone and high torque zone, which is starting application, especially in Indian traffic conditions, stop and go, it gives you around 30% efficiency. So even it does not show that, the PMSM also are very less efficient in very low RPM and high torque zones, which causes the problem. So when you expect your vehicle to perform very well, gives very good range, even the PMSM, it does not give you, because you're not operating in the peak operating zone. Forget about induction motor. Any which ways you have poor efficiency in this region, right? So people what started doing it, people started thinking as a system level approach. Again, a vehicle does not work on a standalone component. It works as a system, as an integration, which matters the most, right? People started thinking about two-speed transmission, three-speed transmission, four-speed transmission. Bajaj recently came up with your EV, which two-speed transmission, right? People know about it. Metal also started giving. Even for the four-wheeler trucks application, people started using multi-speed gearboxes, just because the start and go condition for EV PMSM motor also gives you poor range. They wanted to shift this to a higher efficiency zone just by using a gear ratio in between. So when you operate in first gear, you actually tend to reduce your torque requirement there, and you try to be on the higher efficiency zone by using gearboxes. People initially thought the gearbox may not be sound, but eventually they're trying to realize that. And induction motor also, if you see, you can actually make it operate also at a more efficient zone by using a right gear. Because if you're operating at by the using a gear ratios, you can operate the motor. Even the vehicle is operating at low speed, you can operate the motor at very high RPMs at peak efficiency zones, right? By you, and then since you're using a gear ratio in between, the torques also will come down. This is just an input. So are you enjoying this? Are you people learning something new? I want to get a yes or no on the chat. Although I think now I messed it up somewhere. Yeah. Are you finding learning something new? I want to make sure that no one is sleeping. Okay, very difficult task Priyakshi has given to me today. Okay. Let's go in detail of this furthermore, understand with some classical examples in the real world EVs, right? So this is data which is directly data people published. So they had this range, what you call it, MIDC part one range. I was myself responsible for all the range and everything for that Mahindra also. Coming back on this, so urban condition MIDC part one, MIDC part one, part two, which is called UDC and EUDC combined gives you 390. But real world application, they themselves publish, even though I'm saying that my range is an MIDC part one is 465, on the real world, you will get a range between 290 and 310, right? And when I'm trying to increase the battery capacity by 10 kilowatt hour, my range will only increase by 80 kmph or 80 kilometers. Although the certified range may increase by 140, but if you see on-road range is not increasing by that much, right? Because again, it is real world condition and you have stop and go condition, high speed drivings and all those things. Let's understand in more detail with classical example what is happening over here, right? So this is basically Nexon. If you can consider this one first two rows which are there, the price difference between these two is around 1.5 lakh rupees and battery capacity is around 10 kilowatt hour difference. And whatever the on-road range, what Tata has published, I have taken the higher figure of that because they have taken the AC impact, which I'm trying to neglect just by taking the higher numbers, 310 to 230, right? If you see the difference in the range, which is 80 kilometer between these two numbers, and the price increase is 1.54, right? Now, if you see this, by increasing the battery capacity by 10 kilowatt hour, right, you are able to increase the on-road range by 80 kilometers. That means you are spending somewhere around 2000 rupees to increase the range by 1 kilometer. Does it sound logical to you people? Right? This is how you decide the when you're trying to address the product planning stage, when you're trying to make a vehicle at system at vehicle level thought process, this is what is done. You understand what technology I should use it to increase the range and what's my cost per kilometer range increase. This is that analysis. And this is done for Punch EV, also Tiago LC based on the data which is available, right? Now, let's consider that in this scenario, I've taken an example of Nexon EV. What if you increase the system efficiency of motor controller gearbox just by 2%, just by 2%, right? If you perform simulations, you'll understand if you increase the cycle efficiency just by 2%, the range goes up by 5 kilometers, right? You can do by simulations by yourself also, right? You understand By this method, the range increase happened by 5 kilometers. But now let's assume something that initially the Nexon was having, or maybe having induction motor, did not have the permanent magnet motor, right? Because at this point of time, we don't know what's this price increase, right? It can be by SMCs, what Sajal was talking about. You can use soft magnetic composites instead of laminates. You can use some other technology. We'll talk about all those things, right? Which can give you this range increase. But now you have to understand what's my price increase. Let's imagine, I think you might be aware that Tata Ace EV use induction motors, right? If they move from induction motor to permanent magnet motor, consider that way. So we are considering that, okay, initially Nexon EV has induction motor. If you migrate to permanent magnet motor, what is will happen, right? Why people are not using permanent magnet motors? And I think NRI such Patish also talked about it. They're very expensive, right? And you want to reduce your reliance on the other countries. Let's understand why PMSM is expensive, right? The reason is the permanent magnets at the first place. And we talked about it. I think they covered in the beginning of the session itself, right? And if you see the amount of magnet which is going in different vehicles, it's varying, right? Based on the kilowatt, whatever the motor they have. BMW i3 has 2 kg of magnet. Jaguar I-Pace, Tesla Model 3 has 1.8 kg of magnets, right? The typical rule of thumb is per 100 kilowatt of peak power of motor, there is a 1.2 kg of niobium magnets, right? Niobium, iron, boron magnets, which are there. Typical rule of thumb, right? So if based on this, if you try to calculate for Nexen EV, which has around somewhere around 100 kilowatt of motor, 100 kilowatt of motor, in that case also somewhere around 1.2 kg of magnet will be there, right? Now let's see why magnets are expensive at the first place. Magnets are made of multiple components. The typically percentage ranges from 19 to 35% niobium, then iron, boron, dysprosium, paradysprosium, niobium, aluminum, copper, and all those things, right? Difficult names to remember, but it's okay. Let's see the pricings what they have in the market, right? As per the dollar, as per yesterday's data, I think 2 days back data, the dysprosium was around $400 per kg, right? And if you see the trend of the pricing, if you see just after the COVID, when everyone's thinking about EV, the price was 100 times higher. Can you see this? In Jan 2022, the dysprosium price was $769. It's insane amount of price. Initially, it was not like that, right? When everyone started thinking about at this point of time, at this point of time, people said it's very expensive, right? Similarly for niobium, right? Ni- niobium, if you see that, that is also somewhere around $100 per kg. And same time when this was also around $769 per kg, this was around $220 per kg. Very peak, that point of time, all the OEMs and all the people decided, no, no, PMSM is very expensive, permanent magnets are very expensive, let's move ahead from it. We should make magnetless motors. That's how the demand started coming down, just because of higher prices of this. And just because of the demand started coming down, the prices also of these rare earth materials, REMs, started coming down, right? Now, if you just see based on this, you know the composition now. A typical magnet, the neodymium magnet, permanent magnet. What is the composition? What you can do is for that 1.2 kg magnet which is being used in Tata Nexon for suppose, right? Which you have to use it for that application. You can decide based on the current dollars which are price which is available in the market. You can calculate what is my cost of that 1.2 kg. If I'm going from the induction motor to the permanent magnet motor, what is the actual should costing? So this is how the should costing is done, right? I think people who from the EV sourcing and all, they know the should costing analysis, right? Based on that, you understand, okay, I had increased my efficiency by 2%, which resulted in 5 kilometer range increase. And that I could able to do it by adding permanent magnets in PMSM and including my process cost and everything, about 10%, I was able to increase the price increase by 10,000 rupees. But if you see, the price per kilometer still is comparable to your increasing your battery capacity, which was 2,000 rupees per kilometer, right? Are you getting the correlation? So it's not always necessary. that you should be keep on increasing your battery capacity to increase the range of the vehicle. You can still do it by changing other parameters. You can overall improve the vehicle efficiency. This is what people do, right? And this is a typical graph of for a given capacity, how much range variation is happening from supplier to supplier. If you see a typical 80 kilowatt battery pack, if you see the Tesla is somewhere lying over here with the red dots, Toyota, people are lying over here, right? So they're not able to make very efficient vehicles. That can be because of motor controller, gearbox. People need to think as a system, as a vehicle, rather than a standalone components, right? You should not think only an MC, LFP, or your motor or motor controller or gearbox. Everything works as a system, and everything as a system has to be optimized to get the best results. This is what good OEM does it, right? And its software is also included because the control algorithms also has to be refined to get the best results, right? If you see, that's why the Teslas are very good. Even the Hyundai is also very good. They also use some kind of clutches and all those things. Their Ionic 5, Ionic 6, I have done the personally benchmarking of those the vehicles, very efficient vehicles. They go on the fundamental levels, first principle approach to optimize the vehicles, right? This is from the efficiency perspective. Let's understand now we have done the motor selection, right? Now some people want to ask, okay, what is the voltage I should choose? What is the current level I should choose, right? Typically, this is how it looks like this table. If you're less than 15 kilowatt hour, if your power rating, you can go with 48 volt system. If you are going with around 1525, again with 60 volt system. When you're going beyond 25 kilowatt or sometime beyond 20 kilowatt, and especially depends on your ambient temperature also, because if you are operating in Rajasthan, even if you're going with 72 volt system may not be logical because the currents are quite high, right? So that depends on ambient temperature also. If you're launching this in European countries, this may work out because ambient temperatures are less, natural cooling will happen of system, right? And then you have liquid coolings and all those things. We'll talk about it. Then typically 96 volt base system is used. Tata Ace EV I think is also using 96. They have migrated to 300 I think now. I'm slightly forgetting that. Then typically you will see in the four-wheeler application, people are using 400 volt system. Tata Nexon, Mahindra, all other people are using 400 system. When you talk about more and more efficient vehicles like Tesla, Ionic, trucks, buses, what we have in India also, they use 800 volt system because current rating goes very high, pretty high. The bus bars will be melt otherwise, right? You need to go with the higher voltage system, right? Let's summarize what we have learned right now based on the previous thing. What you could decide based on your system sizing exercises, you could decide the peak power, peak torque, rated torque, right? Peak current, current based on the voltage selection also. We could decide based on the max RPM also, based on the gear ratio and the maximum speed of the vehicle which you're targeting. What's my operating temperature, which is an input point for you, right? My operating voltages. The IP rating is also very important. Are you going with IP67, IP68, IP65, right? Dimension, packaging requirement, weight requirement, cost requirement, efficiency, not only peak, but also cycle efficiency. What is required on that? What my warranty target is 3 years or 30 years, right? Then my thermals, are you going with liquid cooling or air cooling, right? Let's quickly cover the motor controller aspects also, right? We have gone in detail of motor. In motor control also you have, since you will select your motor first, or you should be thinking as selection of a system as a whole, because as a system which matters the most, because we talked about it, some of the motors, their control efforts are higher, right? Although they are cheaper. So the controller will be expensive. So don't think standalone from a motor perspective. You have to think from a system perspective, including gearbox. So three in one combination. So what is happening? The trend OEM are preferring the suppliers who are giving three in one solution, right? I think Akshay also talked about it, right? That is what people are preferring, right? So you have to select based on your overall strategy. What is the controller you're going to use? Are you going to AC controller or BLDC controller? The inverter what you're having is two stage, three stage multi-stage inverter that is control the efficiency of it, torque ripples of it, right? What kind of controls you are having on that controller? It's a PWM control, FOC control, vector control, right? So these kind of thing you'll be deciding. Is a trapezoidal, sinusoidal, right? Is a sensor So because there is a sensorless control also which is becoming very popular, because at the end, at the motor level, you have encoders, you have hall sensors, right? Optical encoders also. So this also adds the cost. People are going away with those also and trying to develop sensorless controls also, right? So the motor has to take care of all the algorithms into play, right? Different functions, as I talked about it, the L5 category of vehicle, if you are thinking in the market right now, they don't prefer using, or especially the low cost two-wheeler, they don't have ECU separately. So all those functions you have to embed in your motor controller itself, right? One thing is the safety and redundancy. And when if you're trying to make a for four-wheeler extremely efficient system, people are going with SiC and GaN based inverter, right? Which is your power electronics component, which makes the system much more efficient, right? Summarizing this with a controller selection summary, at the end, you have motor types, voltage ratings, power ratings. So this is becoming typical SOR for you, right? What you're looking forward from a motor controller supplier. What's my cooling requirement, communication requirement, how much regenerative braking you have, kind of control algorithm what you're using, what kind of safety feature that motor controller is actually giving to you, right? What's the programmability of a motor controller? What's my IP rating of complete system? And then software standard ISO 262, and what kind of soft safety things you have considered or other things, right? This is all from my side. I'll just brief about Techland. So we are a ecosystem of EV. I myself, I really passed out, worked with 12 years in the industry. And my co-founder also, Lokesh, is also from IIT Kharagpur. We both are co-founder of Techlans. We offer training programs, engineering services, right? So engineering services, we offer model-based development, system engineering, MBSC support, analytics and AI, right? So all these things. We have hardcore training programs because we ourselves are core technical people. What programs we have running is Battery plus BMS bootcamp system sizing, and motor plus motor control is also going to get launched in next month. This is all from my side. I think I have not bored you people and I have not extended time too much, Priakshi.